Okay. All right. So for all the other students, welcome to the makeup lecture that we're doing today. Today's lecture, we are going to be covering the Schrodinger equation and electronic configurations. So this is a picture of Schrodinger here. Just a quick introduction to the topics of this module. We talked about the atomic spectra and the Bohr model where electrons orbited the nucleus in specific radii. So this was a kind of a model where the energies of the electrons were precisely known, and then you could say that the momentum of the electrons were precisely known as well. But the quantum mechanical model is a little bit different. We introduced the concepts of the Heisenberg uncertainty principle, which said that basically you cannot know the momentum and the location of an electron simultaneously. You can only predict where they may be with probability density functions. And so this is a marked difference from the Bohr model, or the traditional model of the atom, which was, dated, in the early 1900s. So this is the model that we prescribe to today, and this explains a lot of the behavior of the atoms atoms and electronic behaviors that we see in solid state electronics. So that's why we cover it. So we talked about Heisenberg uncertainty principle last time. We talked about probability density functions last time. I'll just recap that really quick today and then get into the Schrodinger wave equation. We'll talk about the Schrodinger wave equations for the free electron, the potential well, and the single atom. And then we'll get into the electronic configuration of single atoms. Okay, so this will be, I think relatively easy compared to the mathematics here. Okay, I just want to remind everyone that since this is not a class on differential equations, it's not a class in quantum mechanics, some of the treatment of this material is going to be, kind of an overview, a superficial treatment, but enough to understand how they work, their importance in solid state electronics. All right, so let's start by quickly recapping last time. We'll talk about the Heisenberg uncertainty principle and probability density functions. So Heisenberg basically stated that it's impossible to simultaneously measure the momentum and the exact position of the electron. And you can think about it just in terms of this equation, that the product of delta x and delta p is greater than or equal to a constant. There's another form of it too that we don't emphasize too much. This is the one that we talk about more. Position uncertainty times momentum uncertainty. Melvin, as you pointed out last time, momentum and velocity are intimately related. So you can also think about this as velocity uncertainty. Okay, and if you think about why that actually is, I wanted to give you a little bit of an intuition here. I'm going to jump ahead to the wave packets. What does it mean, like when the Heisenberg uncertainty principle says that we can't simultaneously measure the momentum and the position of an electron? What does that actually mean? So let me just delete the ink on this slide. That's okay. Never mind. So we're going to talk about the wave function today. Okay, so an electron can be defined by a single wave function. It could also be described by a sum of wave functions. A wave function is literally like a sinusoid or a cosine. It could be a sum of sinusoids or cosines. Okay, so let's talk about the Heisenberg uncertainty principle again, assuming that the electron location is described by a wave function. What does that mean? Remember, we said that with the wave function, wherever the wave function has a high value, whether it's positive or negative doesn't matter, because the probability density function, which describes its location, is the absolute value of psi squared. Okay, so wherever the absolute value of the wave function is large, that's where we're most likely to find an electron. That's with these yellow shaded regions here. Okay, so if you have an electron location that's defined by a single wave function, the electron could be here, it could be here, it could be here, it could be here. This is this is a wave that goes on forever. And so there's really no certainty in the electron location. But because this is a sinusoid has a defined wave number, defined wavelength. Okay, so there's absolute certainty in the momentum. Okay, so this is an example where there's low certainty in location, high certainty in momentum, i.e. the wave number. And in this example, this is where an electron location is defined by a sum of many, many wave functions. At the extreme, if you add up all the possible frequencies there are, then you end up getting something that looks like a delta function, which is basically just a spike at x equals 0. So in this situation, where your your wave function is a sum of sinusoids, and it looks something like this. Okay, the addition of these sinusoids basically gives you this delta function. In this case, since you have just a spike in the middle, there's a high certainty in the location. That means the electron is very likely to be at x equals 0. But there's low certainty in the wave number because this delta function is the sum of all these sinusoids. So there's a K1, there's a K2, there's a K3, there's a whole bunch of different wave numbers that make up this delta function. So you don't have good certainty in the wave number. Okay, so those are the two extremes. Now, when we actually talk about the Schrodinger equation, most of the times it won't be either of the two extremes. It'll be something in between. It'll be a sum of sinusoids, but it won't be a sum of all the possible sinusoids there are. It won't be all the possible frequencies. It'll be some set of frequencies. Okay, and when you add up a whole bunch of sinusoids, as we saw last time, that are at different frequencies, some set of them, they create something that looks like a wave packet. And we talked about this in class last time, so I just want to touch on it again before we go in here. So this is a bunch of sinusoids up here. You can see, if I'm going to drag this over to the left here, this is a situation where all the sinusoids basically have the same wavelength. Okay, and when they sum up, they create a sinusoid of that wavelength. But when the sinusoids start to have different wavelengths, then the sum of them starts to look more like a wave packet. A wave packet is 0 outside the middle, but then right in the middle, it looks like a sinusoid with the maximum amplitude in the middle, and it decays as it goes away. So this is useful for describing a location of an electron, because wherever there's a non-zero value, the electron has a possibility of being there. So this is basically telling us that the electron is residing somewhere in the middle here. Okay, and it's also telling us that the electron has some kind of wavelength associated with it. Okay, so it's giving us actually two pieces of information, and this is where the concept of, like, you think about the electron as a particle residing at a specific location. So this kind of tells us a little bit about that. It also tells us the electron behaving as a wave because it has a wavelength associated with it. Okay, so since a wave packet is composed of many different sinusoids, there's some uncertainty in the wave number. And because it's not a delta function, because it's spread over a range of x, there's not absolute certainty in the position either. Okay, so the wave function kind of tells us approximate locations and then approximate momentum of the electrons. Okay, all right, so the Schrodinger equation is what we're going to talk about today. Is an equation which basically allows us to figure out the wave function. It allows us to derive the wave function. Okay, we're not going to do a full-out analysis today, or full-out derivation. We are going to do kind of like just well, it's going to seem like a lot of mathematics, but it'll just be, I'm going to walk you through the different steps and show you the intuitions that goes to deriving the equations without getting too much into the math. Okay, so as I mentioned at the end of class last time, the really cool thing about the Schrodinger equation is that it starts off with just a simple equation of classical mechanics of an electron. Kinetic energy plus potential energy equals the total energy. And this statement corresponds to these two examples. Okay. An object can have potential energy, it can have kinetic energy, and the total energy is the sum of the two. We talked about the gravitational example. We talked about the electrical example. In the electrical example, just to remind everyone, the potential energy is voltage times the charge. Imagine that you have a charge in a parallel plate system where there's an electric field. That electric field accelerates the charge. And as the charge accelerates, some of this potential energy is converted into kinetic energy, and that kinetic energy is 1/2 mv squared. All right, total energy is equal to kinetic plus potential, and that's what the Schrodinger equation starts off with. So then what happens is, by applying some quantum mechanical operators and taking into account the de Broglie equation, we can come up with what's called the quantum form of this equation, where the kinetic energy and potential energy and total energy, it is transformed by quantum mechanical operators into a differential equation that has this psi in there. And that psi is the wave function. All right, so just remind ourselves what the different parts of a differential equation are. Does anyone remember what this is? Del squared. So this one is it's called the Laplacian operator. You can kind of think about this as a second derivative, and it's a spatial derivative. You can take the derivatives with respect to time. You can take the derivatives with respect to space, like x, y, and z. So this is the second derivative with respect to space. D squared psi dx squared, d squared psi dy squared, d squared psi dz squared. Then there's another factor here, which is the function psi again appears, multiplied by the potential energy, and there's a d psi dt term here. Now, anytime you have d something dt, the derivative with respect to time, that means that if you look at the steady state behavior of the system, this can go to you can turn this factor to 0. Okay, but so let's get into a little bit of the details of it. So what does this do? It gives us this wave function that describes both the energy and the position of the electron. And what do we have to plug into the equation to figure this stuff out? You have to plug in a potential field, and that comes from the atomic structure. So the Schrodinger equation links atomic structure to the wave function, which tells us about the electronic structure. All right. So I want to talk a little bit about the simpler forms of the Schrodinger equation for specific cases. So we're going to be doing a little bit of work with the Schrodinger equation in the one-dimensional system, not in the three-dimensional system. It's a little bit too complicated. That's more for a math class. So we're going to take the three-dimensional Schrodinger equation and we're going to convert it into a one-dimensional form. Okay, so the typical three-dimensional Schrodinger wave equation is a function of x, y, and z, and it's also a function of time. Okay, so this is the equation that you saw on the previous slide. If we take the x dimension only, okay, then psi basically becomes a function of x. So we have a one-dimensional system. Now, the real world isn't one-dimensional. We're just doing this so that we can gain a little bit of intuition about how the Schrodinger equation works. So if we take the x dimension only, we get the one-dimensional time-dependent Schrodinger equation. All right, and see what happened here is that this psi square, this del squared term, which is the Laplacian term, that basically became the second derivative with respect to x. So this y term and the z term disappeared, and this is only now a function of x. Second derivative with respect to x. Okay. Now this term, we're just denoting the v basically continues down here, but we're just denoting that v is now only a function of x, not a function of x, y, and z. And psi is a function of x and time. Okay, so now if we continue to simplify this further, this just continued down here. If we continue to simplify this further and we look at an even simpler case, a one-dimensional steady state case, what's going to happen in the steady state? Which of these terms is going to go away?
d psi xt dt.
Yes, exactly. So this whole term on the right-hand side is going to go away. All right, so when this term goes away, and then you can use a technique called separation of variables, which we won't get into right now, and you get this one-dimensional time-independent form of the Schrodinger equation. And this is a version that's a little bit easier to work with, and we can do some example problems that give us a little bit of an intuition. But keep in mind that real atoms and real things are based upon the three-dimensional time-dependent Schrodinger equation. Okay, this separation of variables, by the way, this is a technique used in differential equations where a function, you make an assumption that it's a product of two functions, a function of x and another function of t. So I don't want to get into all the details of that because, like I said, this is not a math class. Okay, so let's derive this time-independent Schrodinger equation, the 1D time-independent Schrodinger equation. Okay, so we're going to start off with this very simple statement. The kinetic energy plus the potential energy is equal to the total energy. Okay, and we're going to kind of go through the step by step how we can obtain this one-dimensional time-independent form of the Schrodinger equation. Okay, so the reason we're doing this is so, again, it's about intuition. We want to gain some intuition of wave-particle duality by showing how this statement up here, which is kind of, we think about this in particle form at the beginning and we transform it into a wave form at the end. I'll say that again because it's a very important statement. We take a statement like this, which looks at kinetic and potential energy in assuming that it's a particle, and we transform it into a wave equation where it exhibits wave-like properties. Okay, some of the key intuitions here, we'll touch on these again, but the conservation of energy holds true. We'll get to some of these other ones in a second. Okay, so we start off with K plus U equals E. And again, treating this completely like a classical particle system, the kinetic energy is equal to mv squared over 2. Okay, and remember that momentum is equal to mass times velocity. So we can put kinetic energy in terms of momentum here, p squared over 2m. Okay, classical mechanics here. So this k becomes p squared over 2m. And the u and e just come down as before. So that's the first step. Now the next step is incorporating the de Broglie equation. All right, right now we have an equation that just describes essentially a particle. But now we're going to say, hey, you know what? This particle has a de Broglie wavelength associated with it. So it can be described by some kind of sinusoidal function that has a wavelength. So the first thing we want to do is say, like, okay, the de Broglie equation, just to remind everyone, it relates momentum to wavelength. Okay, the de Broglie equation relates momentum to wavelength. So we go back. So we go back here and say, well, this thing has momentum. So let's see if we can find the de Broglie wavelength. All right, so we just have the de Broglie equations here. Wavelength equals h over p is equal to h over mv. And then, you know, we also found that the momentum is related to the wave number. Momentum is equal to h divided by lambda. And then lambda is equal to 2 pi over k. It's the definition of the wavelength in terms of wave number. So the momentum is equal to Planck's constant with a bar across it. That means Planck's constant divided by 2 pi multiplied by the wave number. Okay. So based on that, now we've put this in terms of the wave number. So we took momentum and we transformed momentum into the wave number. So we're already starting to rethink about this equation in terms of a wave. Okay, now the trickiest part is this, and this has to do a little bit what has to do with the derivatives of the wave function. Okay, so this little section here is called the derivatives of the de Broglie wave. Now we are going to assume that the electron can be described by a wave function. A wave function is a sinusoidal function. Okay, so a basic sinusoid, a times sine of kx. So the wave function is some sinusoidal function with some wave number k and some amplitude a. Okay, we're just kind of assuming that it behaves like a wave. Now let's see what happens. So mathematically, if you take the derivative of a sine, you get a cosine, right? The k comes out here, so you get ak cosine of kx. So the derivative of a sine is a cosine here. If you take the second derivative, okay, so we took the first derivative, now we take the second derivative. The derivative of a cosine is a sine. Okay, so you take the derivative of this, you get a times k squared sine of kx, and you have a negative sign here. All right, so we're just taking some derivatives here. Now a key intuition is the second derivative is a sine, and the original wave function was also a sine. Okay, so it turns out that the second derivative, the wave function and its second derivative are related to each other. In fact, the second derivative is just equal to k squared, -1 times k squared times the original wave function. Interesting, right? So the second derivative ends up being just a constant squared times -1 times the original wave function. Okay, this is a key mathematical trick, I guess you could say. All right, so so now we're going to use this fact and plug that into this equation here. So what that means, if we solve for k squared here, k squared is equal to 1 divided by psi of x times the second derivative of psi of x. Okay, that's just rearranging this last equation. So why do we do this? This k squared is what we're going to plug in here. Okay, so we plugged in basically the wave equation. We substituted that in for k squared. All right, so that's how we go from a basic statement of kinetic plus potential energy for a moving particle. We assume that particle has a certain wavelength and behaves like a wave, and prescribe that can be described by a sinusoidal wave function. And then we can come up with an equation, a differential equation that depends on that wave function. So we've transformed our statement of kinetic plus potential energy is equal to total energy, but now we have it in the form of a wave function. Now, if you do a little bit of rearranging of this, you get it into this form here, the form that we saw in the previous slide. And this is kind of the standard form of the one-dimensional Schrodinger equation. Okay, so now that we kind of got a bit of an intuition about where this came from, now we can look at how we're going to use it. And this is the overview of how we're going to use it. Let's say we have some kind of atomic structure. That atomic structure is going to give us an electrostatic potential field. And these are the boundary conditions of the Schrodinger equation. In order to solve the Schrodinger equation, you must have boundary conditions. You can think about this as the input to the Schrodinger equation. Once you solve the Schrodinger equation for this set of boundary conditions, the output that you get is a wave function. A wave function is a three-dimensional equation that describes the location and energy states of an electron. And this ultimately gives us the electronic configuration, and it determines the electronic properties of a material. Okay. I'll stop here for a second. Do you have any questions thus far? Okay, no questions yet? Okay. All right, so first example is a free electron. We want to understand how the Schrodinger equation works. Let's assume a free electron. Free electron means that there's no electrostatic potential field. What do I mean by that? We'll go into this a little bit later, but I just want to give you the brief overview of it right now. Oh, my pen's not working today. Let me see if I replace the battery, if that helps. Okay, well, I'm going to do my best to draw with the mouse here right now. So whenever you have a positive charge like this, okay, this gives off a potential field. Okay, the potential field is strongest near the positive charge, and it goes down the further away you go from it. We'll talk about that more in a second. All right, so you think about like the atomic nuclei having positive charge associated with it. So when you're close to the nuclei, the potential is high. When you're farther away, the potential drops off. So in this first example, we have a situation where the potential is zero everywhere. This means a free electron, there's no atoms anywhere. Okay, so in this case, the boundary condition that goes into the Schrodinger equation is basically zero. We're doing a one-dimensional example, by the way. Okay, so this goes into this 1D steady state Schrodinger equation. And this is what the equation looks like. So the first thing we're going to do is we know that this v of x is equal to 0. So this term goes away. And we're just left with this. Okay. Second derivative of psi multiplied by some constant times psi is equal to 0. So it turns out this is a common form of a differential equation. Does anyone remember this from before?
A little bit.
So this is like a classic form of a differential equation where you have the second derivative the second derivative of a function, and then you add that with the original function, and then you have a constant in front of here like this. So because this is a very common form, there's already a solution for it. So we don't have to bother solving it. We just have to figure out what some of the constants are. Let's put it that way. Okay, there's known solutions to this differential equation, and the solution form looks like this. Remember, we're trying to solve for psi of x, right? We're trying to solve for this guy. So the solution form looks like this. Psi of x is equal to a1 cosine of kx plus a2 sine of kx, where k squared is equal to 2me over h squared. So basically, this is k. Actually, this is k squared. So k is the square root of that 2me over h squared. Okay, so we just took, this is a standard form of a differential equation. So when we solve differential equations, what we do is we take a solution form like this, and the solution form has a couple constants in there, A1 and A2, and then it also has this K factor in there. Okay. Now, yeah, this is not correct. Let's just cross this out. Now, in this case, we said there's no boundary conditions, right? It turns boundary conditions are what are used to figure out what A1 and A2 are. So we don't have any boundary conditions to constrain these two. And in fact, here, let me just, we don't have anything to really constrain K either. This is a little bit more of a subtle point. So as a result, there's an infinite number of solutions. So we can basically say psi of x is equal to A1 cosine of kx plus A2 sine of kx. And A1 and A2 could be any value. K could be any value. Okay, there's nothing constraining it. So if we look at what K is equal to 2me over h squared. So what this means is that if you can have any possible value of K, you can have any possible value of E. M and H are just constants. So, those are just fixed numbers. If you can have if there's nothing constraining your K, then there's nothing constraining your E. What that means is that electrons can exist at any energy. Any energy. And in quantum mechanics, we say that there's no quantization here. Okay. Everyone with me so far, give me a thumbs up if you're following. If you have any questions, we can stop here for questions. Good.
I have a question though.
Yeah, go ahead, Corey.
Are you able to use that K equals square root of 2me over Planck's constant squared? Are you able to use that and the 1D wave function, the E equals Planck's constant squared K squared over 2m to, I guess, find a K or an E if they're unknown?
If you say that the K, the wave number, remember the electron can exist at any wave number and at any energy, right? But if we said that, if the electron has this specific wave number, then we could calculate the energy of the electron.
Oh, okay. Okay.
Does that make sense?
Yep.
So all that's being said here is that there's nothing constraining E or K. So the electron could exist at any energy.
Gotcha. Okay.
So in free space, there's no discrete energy states. Like, how the Bohr model said, electrons can only exist at certain energy states. That's not the case with free electrons. We'll find out in the next example that if you have some boundary conditions, and that actually limits the number of states that energy states that an electron can have. So let's go on. So this is the next example is called a one-dimensional potential well. Okay, and there's two slides on it. The first slide is kind of the overview. The second slide, we go into a little bit of the math of it. So this is another example of the Schrodinger equation. Now, this is sort of a hypothetical situation where, let's say you had, sorry, this drawing is not going to be great. Let's say you had a positive charge here and a positive charge here. Okay. So then wherever there's a positive charge, there's infinite potential. So there's infinite potential here, and then there's infinite potential here. So we haven't talked a lot about what electrical potential is. So if that seems a little bit confusing to you, just take it at faith right now. Okay, wherever you have a positive charge, right at that point, the potential goes to infinity. In between there, the potential drops off like this. And so the potential for this type of situation would look something like this. If we were to graph the electrostatic potential, it would look like this. Okay, where this goes to infinity here and it also goes to infinity here. So this is your position x. And this is v of x. Now, this is a more complicated function. It involves more math. A simplification of this type of situation is what's called the classic potential well, where you have infinite potential at x equals 0 and infinite potential at x equals L. And L is the distance between these two positive charges. Okay, so this is kind of like one of those hypothetical exercises to help you understand the Schrodinger equation. It's a gross approximation of what actually would happen in an actual atomic system, right? But we're trying to build up our understanding right now. So in this type of situation, the difference between this one and the previous one is that you actually have a defined potential here. Before, the potential was 0 everywhere. In this case, the potential is 0 inside the well, inside here, and the potential is infinite at x equals 0 and x equals L. Okay, so that's how it's defined here. When we plug this into the Schrodinger equation, these are boundary conditions that we plug in, we will find that the solution is a set of wave functions where it's not any arbitrary sinusoid or any arbitrary combination of sinusoid. It's only certain sinusoids can, the electron can only exist in certain sinusoids, and that corresponds to specific energy states. The electron can only exist at specific energy states, and each energy state is described by a wave function. So these are 3 sinusoids you can see here at slightly different frequencies, right? Slightly different wavelengths. So this is just illustrating the first 3 solutions to the Schrodinger equation in a 1D potential well. Okay, so we'll go into some of the details of how this is solved. I'm just going to put this all out on here, and we'll go through it step by step. Okay, so the possible solutions to the 1D Schrodinger equation are a set of sinusoids, each with the corresponding quantum number n. Let's see where that comes from. Okay, so we had our boundary condition here. Again, boundary condition, voltage, the potential is infinite at x equals 0, infinite at x equals L, and it's 0 everywhere else. So we plug this into the one-dimensional steady-state Schrodinger equation. Okay. The v of x term goes away because everywhere within here, the potential is 0. Okay, we're just ignoring x equals 0 and L for the time being. These are boundary conditions. So this will come into play when we do our boundary conditions. But when we solve this equation here, the v of x is equal to 0 everywhere else. So you just basically remove this, and you're left with this basic equation again. This is a classic form of a differential equation, same as before, same solution form, okay? So the difference this time is that we have boundary conditions that will restrict the solution. What are those boundary conditions? The wave function is equal to 0. The wave function is equal to 0 at psi equals 0 and at psi equals L. Okay, now you may be wondering like where that came from. Is a little bit of an intuition that if the potential is infinite, the electron cannot exist there. Okay, so I don't know how do you want to think about it. Whenever you have a charged particle that has where there's an infinite amount of potential energy, the charged particle will want to go away from that spot. Okay, that potential energy will be converted to some kinetic energy, and the particle will not stay there. So basically, like what this is saying is that the electron cannot exist at places where there's infinite potential. The reason why this is called a potential well is because the electron is essentially like stuck in between these 2 regions where the electron can't exist. Okay, so psi is psi of 0 is equal to 0. Psi of L is also equal to 0. Okay. All right. Now, what that results in, it has some important implications. Let me see if I can get my pen here to work. One minute here. Just bear with me. All right. Fortunately, this does not look like it's working. Okay, good, got it. Okay. Can everyone see my, I guess everyone can see my scribbles here? Just give me a thumbs up if you're able to. Good. Okay, so is everyone following so far? Is there anything, any points of confusion so far? Okay. So if we have these boundary conditions, I'm just going to write this small on here. So if psi, let's use this first boundary condition, psi of 0 equals 0. Okay. So that means A1 times cosine of kx. We're at x equals 0, so this is k times 0. Just erase this. So it's A1 times cosine of 0 plus A2 sine of 0 is equal to 0. All right. So the sine of 0 is 0. It's always 0, right? So this, now we're left with A1 times cosine of 0 is equal to 0. What's cosine of 0? Think back to your trig.
Right?
It's 1, right? So this is saying 1 times A1 is equal to 0. So the only way this can be true is if A1 is equal to 0. So that's where we got this constraint from. The second boundary condition is psi of L is equal to 0. So that means A1, oh, we know A1's 0, so we can just get rid of that. A2 sine of L k times L is equal to 0, right? Sine of kx equals 0. At x equals k, we're left with sine of k times L. So this is the second boundary condition. A2 times the sine of k times L has to equal to 0. The only way this can be true is either A2 is 0. That doesn't make sense because that means our wave function would just be 0 everywhere. The other possibility is if sine of KL is equal to 0. Okay, and that's where the second condition comes in. Okay, think about where sine is able to be 0. So I'm just going to draw this up here so you see. in the unit circle, right? So sine is the opposite over the hypotenuse, right? Sine of x is equal to 0 when, or let's not say x so it's not confusing. Sine of a is equal to 0 when, what are the values of a where sine is equal to 0?
Should just be whole numbers, right? 1, 2.
Not quite. They're multiples of just think about this again. Where would the sign be? The signs be 0?
1
At what
pi,
angles?
1 pi, 2 pi.
Exactly.
3
Yep.
pi.
Pi, 2 pi, 3 pi. Right. Basically n times pi. Any integer times pi, the sign is going to be equal to 0. So that's where this constraint comes from. KL is equal to n times pi. So whatever's in the parentheses here has to be equal to n times pi in order for this differential equation to meet the boundary condition. So that's where this 1D wave function solution comes from. So the solution looks like psi of x is equal to square root of 2 over L sine of n pi x over L. So this is where the n pi came in. From this KL is equal to n times pi, you just rearrange that and that you get n pi x over L times x. And so this is your solution. If you graph out a few different values of this, remember n is an integer, n equals 1, 2, 3, 4, and so on. If you graph out the first 3 values of this, n equals 1, 2, and 3, these are the sinusoids that you'll see. Okay. So what do you notice about these sinusoids at x equals 0 and x equals L?
They're 0.
They're 0. Yeah. So it's a good check. Like when you graph them, you see that it meets the boundary condition. All these sinusoids are constrained to be 0 at x equals 0 and x equals L. So this is how we get how our solutions start to become constrained. Electrons can't exist in any random sinusoid or any random cosine. They can't be described by just any arbitrary sinusoidal function. It has to be at a specific frequency or specific wavelength that the electrons can exist at. And these specific wave functions correspond to specific energy states. So that's what we're getting at here. Discrete energy states that the electron may have. Discrete energy states corresponds to discrete sinusoidal waves that describe the electron. Okay, so each one of these sinusoids here have a different energy associated with them. Okay, and that energy, you're going to need this for your homework, is equal to n squared times pi squared times h squared over 2ml squared. Where does that come from? It just comes from here. K equals the square root of 2me over h squared. So if we know what our k is, our k is whatever's in the parentheses, whatever's in the parentheses multiplied by x. So this k is equal to n pi over L. All right, and that k is related to the energy. So this is where we get our equation for the energy. So what is this telling us? It's telling us as n increases, as we go higher and higher in n, the corresponding energy increases as well. So as we go to higher values of n, the energy of that electron increases. In fact, it increases as n squared. Okay, so a recap of what the solution means. Each solution corresponds to an energy state which can be occupied by an electron. higher frequency solutions corresponding to higher N, it corresponds to a higher energy state. Multiple solutions, that means that there's multiple states an electron can occupy. And in this example, we're considering just one of those states. Let's say we consider the psi2 solution. Just ignore the psi1 and psi3 in this example. So if we take the psi2 solution, which looks like this blue line here, okay, that's psi2. In order to find the probability density function, telling us where the electron is located, we have to take psi2, absolute value of psi2 squared. So this blue line here, which looks like a sinusoid here, after you take the absolute value and square it, it looks more like this. So it's 2 humps on the positive end of things. Okay, now just looking at this, what locations are the electrons most likely to be near? Looking at this probability density function.
L over 4 and 3L over 4.
Exactly, right. So these two regions here, oops. The electron is likely to be in this yellow zone. It's likely to be in this yellow zone. Yeah, Melvin, you have a question?
Oh, yeah, actually, it was,
Go
I
ahead.
just wanted to ask it more so towards the end of the last slide,
Sure.
which had to do with when you said that, you know, each one of these ends corresponds to an energy state. And the now I know in this situation, when we deal with the potential well, we're not looking at an atom, but let's say we were looking at an atom, some hypothetical atom that had a potential well. Could we say that if this atom has 5 energy states, we can constrain the solution to 5 different psi functions?
Yeah, absolutely. Yep.
Okay.
Yep.
So it wouldn't be an
You got
infinite
it.
number of psi functions, it would just be 5 of them, given that the electrons have 5 orbitals in this configuration.
Well, but keep in mind, N goes on forever, you know? So maybe I didn't understand your question properly. So I hope I'm not confusing you here. There are like, you know, there could be an infinite number of solutions here, but that doesn't mean that the electron can exist at just any random wavelength. It's a
Okay.
specific list of wavelengths that the electron can exist at, and a specific list of energies that it can exist at.
Okay, I think I understand. So like if we had a atom that had 5 energy states, then we would have pretty much 5 different wave functions that the electron can actually exist in.
Right.
Okay.
No, I just want to clarify one point though, Melvin, is that an atom actually has an infinite number of energy states.
I didn't know that. Oh.
Yeah. But here's the thing though. We're going to talk about this later in the lecture, is that the electrons occupy the lowest energy states first.
Okay.
You know, so the reason why you don't see an electron at energy state, you know, energy level 1,500, just a tongue-in-cheek example here, is because like the electrons like to exist in lower energy states.
Okay, I got you.
Yeah.
Thank you.
Yep. Okay. All right. So if an electron that happens to occupy this psi2 energy state, that means that the electron is likely to be near L equals 4 and 3L equals 4. So different wave functions describe different energy states, and also it tells you some hints about where the electron may be located. So that's why the wave function is very useful. All right. So these regions are actually called orbitals. We'll talk more about the shape of the orbitals later, but in this simple one-dimensional example, you can see that the electrons are more likely to reside at L equals 4 and at 3L equals 4, less likely to reside near L equals 2. So that's why we can kind of get a shape of like a shape of a region, an electron cloud region where the electrons are more likely to be. Okay, so now we are transitioning. We're going to talk about the Schrodinger equation for a single atom. Before we were looking at the Schrodinger equation, a simple one-dimensional example of the Schrodinger equation in a potential well. We also did a free electron. But now we are doing the three-dimensional Schrodinger equation for a single atom. Okay, and what is a single atom? A single atom is, so let's take hydrogen. So hydrogen has one proton in the nucleus. So it looks like this. Okay. Here, I'll draw it here. So this is hydrogen. So just imagine that positive charge residing at the origin in this graph. Okay, and this is in a cylindrical coordinate system, not XYZ. It's in a cylindrical coordinate system. That's why you see R, theta, and phi. Okay. You know, I could spend a lot of time talking about the different coordinate systems, but I just don't, you know, I just don't think we have time for that right now. But basically, it's another way to describe a point in space. Every point in this three-dimensional space can be described by a radius, an angle from the z-axis, which is called the theta, and an angle from the x-axis, which is the phi. So Schrodinger equation takes in, you have to provide a v of, you know, you have to provide a v, you know, an electrostatic potential as a boundary condition. So what does our V look like in this case? Well, electrostatic analysis would tell us, and this is, you know, if you've taken a class in electromagnetics before, you may recognize this equation, is that the electrostatic potential depends on how far away we are from this, this positive charge. At the positive charge, the electrostatic potential basically goes to infinity. And the farther you go away from this charge, the electrostatic potential drops and essentially goes to near zero. It's a 1/r function. So this is the important thing to remember here. The electrostatic potential drops off as a function of 1/r, where r is the distance from, you know, from that positive charge. These other constants here, this is your Q, you know, 1.6 times 10 to the negative 19, 4 pi epsilon naught. This is the permittivity of free space. It's also a constant. Okay, so we just have a different electrostatic potential condition that we plug into the Schrodinger equation. And now what we get, you know, denoted by this question mark here, is a much more complicated solution. We were looking at just simple sinusoids here. This, you know, the solutions were basically these very simple sinusoids. And in this three-dimensional case where you actually have an electrostatic potential thing in the middle, it looks a lot more complicated. And I'll touch on it a little bit. Let's make sure that we mind our time here. 4:35, okay. So we could start off with the time-independent Schrodinger equation in spherical coordinates. Notice this looks very similar to the x, y, z, except we just have psi being as a function of r, theta, and phi. Okay. This first term is a Laplacian operator. The way that we use to solve this differential equation is a method called separation of variables, where we say that this psi is a function of r, theta, and phi, the three space variables, and we kind of assume that it can be expressed as a product of three different functions, and each of these three functions are corresponding to each one of the space coordinates. So there's a function of r, a function of theta, and a function of psi. So if we assume that it is a product of those three functions, then we have this big long thing here, and this is the three-dimensional Schrodinger equation for a single electron atom, like hydrogen. We plug in the boundary condition that we found for hydrogen, the electrostatic boundary condition. And this is what we get. These are the solutions. Okay, so the solutions here are, somewhat more complicated, but I want you to see that in a lot of ways they're similar. Conceptually, they're similar to what we saw before. Okay, just to make the connection, we basically found in the one-dimensional case there was a series of sinusoids. Okay, and the different sinusoids had different wavelengths. And basically, it was a list of a whole bunch of sinusoids, and that list was basically indicating what are the different possible energy states of an electron. In this case, it's very similar. There are different wave functions that the electron can exist at, and those wave functions are described by this equation here, R of R, there's these three functions that we talked about before. The psi function is a product of those three functions. Okay, so if you want to find the wave function, you have to multiply this column by this column by this column. Okay, so one of the rows in this table, a single row, corresponds to one solution to the Schrodinger equation. Okay, and each one of these solutions has an associated quantum number. Just to make the analogy here, in the one-dimensional potential well, we just said there's solutions. Each solution has a corresponding number n. Okay, and the energy of the state corresponds to the n. In the three-dimensional case, we actually have three numbers like that, n, l, and m. Okay, each corresponding to, like, the fact that we're in 3 dimensions. That's why we have these three different quantum numbers. And there are specific n, l, and m where a solution can exist. So the first possible state is where n is equal to 1, l is equal to 0, and m equals 0. The second possible solution is when n equals 2, l equals 0, m equals 0. You cannot choose any arbitrary combination of n, l, and m, and there will be a corresponding wave function. There's only certain combinations which are allowed. We don't have the details to go in. We don't have the time to go into the details of why that's the case, but just take that at face value. Okay, so these numbers here are called quantum numbers. The first quantum number n denotes an energy level. That energy level is, you can think about it as being related to, the energy levels from the Bohr model. Energy levels 1, 2, and 3. The L and M describes orbitals or suborbitals. We'll talk about that in a second. And then there's a last quantum number S, which describes electron spin. Electrons can have a spin up or spin down. Again, we don't have the time to get into all the details of that. What it does mean is that for each one of these wave functions that you see here, for each value of n, l, and m, each combination of n, l, and m, 2 electrons can exist at each one of these rows, each one of these different wave functions. 2 electrons can exist. 1 electron is spin up and 1 electron is spin down. Okay, so this corresponds to a concept that 2 electrons can occupy an orbital. Just so you don't get confused, there's something called the Pauli exclusion principle. Okay, the Pauli exclusion principle states that no 2 electrons can occupy the same energy state. Every electron has a unique quantum number. So an orbital has an N, L, and M defined. Okay, so every row in this table corresponds to an orbital, a certain wave function. And 2 electrons can reside in each one of these. One that has a quantum number S equals positive 1/2, and another one with quantum number S equals negative 1/2. So every electron has a unique quantum number, and every orbital has 2 electrons in it. When you're doing an example problem on this, you'll see that this A0 is reference to the Bohr radius, and there's an equation for that here. And just like before, when we were doing the one-dimensional case, we said, well, depending on what the n is, we can determine what the energy of the electron is. Similarly here, there's an equation that tells us what the energy level is, what the energy of an electron is based on that number, quantum number n. So an electron at energy level n has this energy given by this equation here. All right, more dense math stuff, but I hope this conceptually, this stuff is making sense. So once you have these functions here that describe the state of an electron, the different states of an electron, then you can think about calculating the probability densities. The probability densities, remember, tell us where the electron is likely to be. Again, analogy here is we found a psi function, in this case psi 2, and then this psi 2 tells us where the electrons are likely to be found. So we're doing the same thing for the three-dimensional case. By the way, you won't be expected to derive this stuff, okay? So the question is, where is the electron? Now that we know what the wave function is, how do we find where the electron physically is located? To calculate the probability of finding an electron in three-dimensional coordinates, we have to integrate the wave function in 3 dimensions. So the three-dimensional probability density is given by, psi squared dv is equal to the product of these 3 functions squared. And we have to integrate this over 3 dimensions. Now, again, your eyes may, gloss over here, but I just want to remind you that these 3 functions came from the separation of variables. And this part here comes from when you integrate something in spherical coordinates, these extra terms show up when you do the integration in 3D. Okay, so that's where some of these terms are coming from. You won't be asked to derive this. If you just want to calculate the radial probability, meaning like if you want to calculate the probability that the electron is between radius r1 and radius r2, you can use this equation here. The radial probability density is equal to r squared, the radius that you're searching for, and then you have to plug in the equation from the previous table, and then you have your dr here. This is the radial probability density, and in order to calculate the actual probability, you have to integrate that according to r. So just remember this equation, because this is what you're going to be using in one of the, I believe in the last problem of the homework. So think about a little bit of intuition here. These are some examples of the radial probabilities in different energy states. Again, by analogy here, in this one we had 3 different energy states. In the psi 2 state, the electron is likely to be at L equals 4 and 3L over 4. If you're looking at the psi 1 state, it's more likely to be at L over 2, right? So depending on what energy state the electron is in, you can kind of determine where the electron is most likely to physically be located. Same thing for these 3-dimensional situations. If you're in the state n equals 1 and L equals 0, the electron is likely to be near a sub 0, which is like 1 Bohr radius. And the probability goes down the further you go away. And the probability also goes down the closer you get to the nucleus. All right, this is radius from the nucleus. If you're at the n equals 2 state, the second energy level, then the electron is more likely to be near, in this region, 5 or 6 Bohr radii. And it might also there's also a smaller probability that it might be close to A0. Okay, and when you get to n equals 2, L equals 1s, you can see a different shape here. So all these different energy states have different corresponding locations where the electron is likely to be. These are all like mathematically derived, but they've been experimentally shown to be true. So this example here, let's see if we have enough time to go over it. I'll just touch on it. Suppose an electron is in the n equals 1 and L equals 0 state. You'll have a problem very similar to this in your homework. So you start off with the equation for P of R. It tells you the radial probability density. This is the part that you look up on the table. Okay, so you have your R squared. This is the portion that came from the table. And then you have your dr over here. In order to find the total probability, you have to integrate. So it's asking you the probability of finding an electron between R equals 0 and R equals A0. So you have to integrate this from 0 to A0. So you have to integrate the function that you found here from this one value to another. And by doing that integral, this is what you find. You can do a definite integral, and that'll give you a probability of 0.32. All the steps here are just doing an integration here. Okay, so I'm just going to skip over that for the time being. This will be a problem like on the homework. The one thing I do want to tell you is when you're doing these types of integrals that have exponents on them, look up integral tables online. Okay, you can, if you just type in table of integrals on Google, you'll find you'll find if you see an integral that looks like it's tricky to solve, just look it up on a table. Again, this is not a math class, so I don't expect you to remember all the different techniques that are used to solve these. Just find it on a table and use it. Okay, so now what do these wave functions actually look like in 3 dimensions? We saw what they kind of look like just as a function of R, but if you plot them out in 3-dimensional space, these are what the Schrodinger wave functions look like for a single atom. And so you'll see these are showing volumes, right? They're showing 3-dimensional volumes, and these volumes indicate where the electron is most likely to be in space. So in this example, we shaded this region in. We said that, well, the electron is most likely to be between L equals 4 and 3L equals 4. So we just shaded in these 2 regions here to just kind of illustrate that's where the orbital is located. In the 3-dimensional case, we're doing the same thing here. We're kind of shading in regions in a 3-dimensional space to indicate where the electrons are likely to be. And these graphs, which, these are just from Wikipedia, it shows the different energy states, and it shows the corresponding orbitals. So the first energy state is L equals 0, N equals 1. And that orbital looks like just a sphere. Once you get into the N equals 2 states, the shapes start to look a little bit different. This one kind of looks like a donut. There's 2 electrons that can occupy this orbital. And then there's 3 more orbitals like this, one in the X direction, Y direction, and Z direction. Each one of these can also hold 2 electrons. Now, so that's kind of illustrated here, the fact that one is orange and one is blue. Okay. And once you get to N equals 3, the shapes of these energy levels just become more and more complicated. You can see that there's a higher number of lobes, which corresponds to higher frequency wavelengths and so on, smaller wavelengths, I should say. All right, so the shapes of the orbitals start to become more and more complicated. So how is this different from the Bohr model? Well, in the Bohr model, we had electrons orbiting the nucleus in nice, neat circular orbits. In this one, we have these clouds. These orbitals describe locations where electrons are likely to be. So sometimes they're referred to as electron clouds. You say, well, the electrons, if it's in this energy state, then it may be on this side of the dumbbell. And if it's in a different state, it might be on the other side of the dumbbell, and so on and so forth. These different shapes are all come from mathematical solutions of the Schrodinger equation. What else do I want to mention here? There's two different notations here. There's the NLMS notation for the orbitals, and there's also the SPDF notation. And so I just have that here. So the SPDF notation goes something like this, and the NLMS notation looks something like this. Let me tell you exactly what I mean by that. This here is one orbital. So each row in this table corresponds to one orbital, or sometimes it's also called a subshell. There's 2 electrons per subshell. Okay. So the 1s subshell, which is shown here, that has an n equals 1, l equals 0, m equals 0. That's in the NLMS notation. So these are the notations for that. But in the SPDF notation, this is just called the 1s subshell. There's 2 allowable electrons in here. When we go to the 2s subshell, it's similar. This can also hold 2 electrons. The 2s subshell looks like this. Then there's the 2p subshell. Now, what you notice here is there's actually 3 lines in the table. Each line corresponds to a subshell, and each subshell holds 2 electrons, okay, corresponding to the pictures that you see here. This is one of the 2p subshells. This is another one, and then this is another one. So notice that these are mutually perpendicular. This one is aligned with the x-axis. This can be aligned with the y-axis, and this is in the z-axis, okay? So you think about 3 dumbbells that are perpendicular, that are arranged in a mutually perpendicular form. So that corresponds to these 3 rows of the column. So a total of 6 electrons in the 2p subshell. So if we sum up the 6 electrons in the 2p subshell and the 2 electrons in the 2s subshell, then we get 8 total electrons at the second energy level, meaning n equals 2. At n equals 1, there was just the 1s subshell, so that's 2 electrons. At n equals 2, there's the 2s and 2p subshells and a total of 8 electrons. In the third energy level, there's actually the 3s, the 3p, and the 3d. That corresponds to this portion of the table. You can see that there's 3 p subshells and 5 d subshells. So for a total of 18 electrons in the third energy level. Okay, and the list continues on and on like this. Okay, so the higher energy levels that you go, there's going to be more and more electrons, or more and more possible states for the electrons. Okay, so that gets us into the last concept. I know we're end up going a little bit over here, and I apologize for that, but I do want to make sure, I just want to finish up this module. And this last part is where we just tie all the concepts together and just do a simple electronic configuration. So this exercise here doesn't involve the Schrodinger equation at all. So it's just a relatively simple exercise. So all that stuff is behind us now. So when we do electronic configurations, basically what we're trying to do is we're trying to see where the electrons are located, meaning what subshells are the electrons in. Okay, and the rules are as follows. So in this graph here, I've kind of drawn out little blanks here, and each one of these blanks corresponds to one subshell. And subshell and orbital, I use the 2 words interchangeably, so don't get confused there. So there's the 1s subshell, the 2s subshell, the 2p subshell, and so on. So the reason I've arranged the lines in this manner is I've arranged it in order of increasing energy. The reason I do that is because electrons always occupy the lowest energy states first. So the first rule when we're trying to figure out the electronic configuration of an atom is to find the number of electrons using the periodic table, start filling up the electrons from the lowest energy states first. And the third rule, I'll get to that in a second, fill a row with one spin before adding electrons of the opposite spin. So let's see, I think we're doing an example of silicon. Let's start with silicon. Can someone tell me what the atomic number for silicon is? Just go ahead and see if you can find it on a periodic table. You can Google search it. So we're doing an
14.
example of silicon. Okay, so the atomic number of silicon is 14. So there's 14 protons and therefore 14 electrons. Okay, so we did the first step here. We know how many electrons we're going to fill in. The next step is fill the lowest energy states first. And so I would go ahead and draw in an arrow here to signify, okay, there's an electron with an up spin. The second electron is going to go in the same subshell, and it's going to have a down spin. So there's 2 electrons in the subshell. Now I go under the 2s level, I fill in 2 electrons there. And then I go to the 2p subshell. Now the one thing to notice here, fill a row with one spin before adding electrons of the opposite spin. So if we're filling in this diagram, we would fill in electrons of up spin first before adding 2 electrons of downspin, before adding the electrons of downspin. Now the reason we do that is because let's say we have 1 electron here and there's another electron that wants to occupy a state. Electrons, remember, they have some repulsion to each other. So an electron, if it sees another electron in this energy state, the electron doesn't like to be near that guy. It's going to go to the next orbital first. It's going to fill up 1 per orbital first before going to filling in the second electron at each one of those orbitals. So you fill up spin first and then down spin. Okay, then you go to the 3s subshells. So how many are we at right now? 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. So we're at 10. So we just did 11, 12, 13, 14. So we just keep on going up the table until we get to the number here of 14. So this is the electronic configuration of silicon. And if we just want to write that down in the shorthand notation, we would say 1s2. Say there's 2 electrons in the 1s subshell. We say 2s2, 2 electrons in the 2s subshell. And we say 2p. There's 6 electrons there, so we say 2p6. We say 3s2, 2 electrons in the 3s subshell, and then 3p2, 2 electrons in the 3p subshell. So this is the electronic configuration of silicon. And you could do the same exercise for other atoms as well. Okay, there we go. It's in here already. So when we actually draw out the energy band, this is actually the energy band diagram. So it's actually showing it's just showing all the possible electron states in order of increasing energy. And so I've kind of drawn it in a very simple form here. So I just want to, I want you to know that I haven't drawn this to scale, okay? It turns out that, here's your 1s subshell here. And then the 2s subshell is way up here. And then the 2p subshell is just a little bit higher energy than the 2s subshell. And then to get to the 3s subshell, there's a big jump, and 3p subshell, there's an even larger jump. So the spacing between the subshells actually becomes a little bit more complicated when we actually start going to atoms. And at some high energy up here, this is called the ionization energy, which means that if an electron gets to that energy level, if it gets to this high energy level, it's actually freed from the atom. And that's what Einstein was showing in his photoelectric effect. you can actually knock electrons off a material if you provide enough energy to that electron. That phenomenon is called ionization. Okay. Just a quick recap of the Bohr model. Remember that a Bohr model was the electrons were orbiting in these nice, neat circular radii, and the higher radii orbits corresponded to higher energy states. So we look at the electronic configuration of atoms. This is a table that pretty much shows it. So helium, as you just start at the atomic number 1, helium or hydrogen, sorry, has atomic electron configuration 1s1. Helium has 1s2, lithium 1s2, 2s1, and it just continues like this. By the time we get to 14, we have like all the 1s and 2s and 2p that's written up here, and then also the 3s2, 3p2. Now, one interesting point I'd like to note here is that once you get past the 3p subshell, electrons actually start filling up the 4s subshell before the 3d subshell. It turns out that the 4s subshell is at a slightly lower energy than the 3d subshell. So it just gets more interesting and more complicated as you go to higher atomic numbers. We're not going to talk about all the details of that. I just want you to know that it exists. Okay, so we're just a few minutes late here, so just want to summarize Module 2. We talked about how electrons behave as particles and as waves. The de Broglie equation was a really important equation that relates this particle and wave-like nature of the electrons. The particle-like behavior is captured by classical physics equations like E equals mv squared over 2. And then you have the equations describing potential energy. The total energy is equal to potential energy plus kinetic energy. And then the wave-like behavior of electrons is captured by the Schrodinger equation, which basically transformed the statement of total energy equals potential plus kinetic. It transformed it into something with a wave equation. And the solutions of the Schrodinger equation will tell us the energy of the electron and where we might physically find the electron. And that is a probability density function. So it tells us basically the electronic configuration of the atom. We did some examples of the Schrodinger equation in one dimension, one-dimensional potential well. Then we did an example of the Schrodinger equation in 3 dimensions where you have an electrostatic potential boundary condition for a single atom, like a single nucleus. And so we saw that the shapes of the orbitals get a lot more complicated, but it's basically the same principle except extended into 3 dimensions. And electrons fill up the lowest energy state first, so you can figure out an electronic configuration for the atoms. Okay, so this module is obviously like very dense. There's a lot of mathematics was involved here. A lot of concepts from quantum mechanics. So I would suggest, get started on the homework as soon as you can. It is set to be due next Wednesday. If you find that you're having trouble with it and need more time, let me know by Monday, and I'm happy to push back the deadline a little bit. But spend time on this, try to understand how to, get a handle on what the Schrodinger equation means by just doing some of the homework problems. The homework/quiz it's set to be due for Wednesday. If you need a little bit of extra time, let me know.
Quick question.
Yes.
The homework, you said you were going to submit it today. Upload it today.
The homework's uploaded already. It should be on.
Okay.
Yeah, if you're not able to see it, let me know.
Okay, and it's due when?
It's due Wednesday, this coming Wednesday.
Okay.
Yeah, but if you need more time, like I said, let me know. We could extend it for a couple of days, possibly till Monday. I don't know if I want to extend it that much, but just let me know where you all are at on Monday. You can let me know during Monday's class.
Thank you.
Yep. So the homework, as I said, is posted. This weekend I'll post the quiz. The quiz is going to be based on the homework where you enter, you enter answers to some questions, and a lot of those questions are going to basically be the homework questions. Okay, Any other questions before we end class today?
I guess about the homework, it says it's out of 150 points, but the homework is it's not graded, you say?
Yeah, the homework's not graded. The point distribution is an artifact from before, but it just gives you a sense for like how the points would be distributed, corresponding to how much work each problem is.
I see. And I guess just one last question, sorry. So, would the homeworks be, I guess, adequate, I guess, practice, say, for the exams, the homeworks, and
Definitely.
maybe going
Yeah.
over the homeworks and the quizzes? Is there anything else that we should look at, possibly anywhere else?
The homeworks and quizzes will prepare you for the exams for sure.
Okay, all right, thank you.
Like obviously the lectures also, like if you go over the lectures, sometimes like students have told me in the past that sometimes there's lectures that have like conceptual points that I sometimes ask for in the quizzes and the exams. You'll see some examples of that in the quiz that you took. You've already seen an example of that where I just ask you some basic like short answer questions, multiple choice questions, testing your understanding of the concepts. Those questions, for some reason, the students find those questions trickier than the calculation problems. Oftentimes they do. So the quizzes will be your gauge for that. If you're able to understand these conceptual type questions that I like to ask on exams.
Thank you.
So, okay. Well, everybody, have a good weekend. Thank you for attending this makeup lecture. It's Friday. Everyone wants to relax. So go ahead and enjoy the rest of your Friday and weekend. I'll see you all on Monday.
All right. Thanks a lot.
Okay.
Have a good
Bye-bye.
weekend.
You
Bye.
too.
Thanks.
Bye.
Bye.